All right. Thank you all for coming. So I won't do an introduction. You already know this gentleman here. So, all right, we are running late. Thank you. Please.
Hello, good morning, everyone. So I am Alexandre Bousse. I am a researcher at the French Institute for Health and Medical Research. And today I will present the work of my PhD students on unsupervised learning for CT and PET reconstruction with generative models. So a lot of things, many things in my talk have been covered yesterday and today, so I apologize in advance for overlaps. So I'll start with a quick introduction on PET and CT reconstruction, then I will introduce diffusion models for image reconstruction, and then I will present all three applications, so motion compensated head CBCT, PCCT material decomposition, and joint reconstruction of activity and attenuation in CT-less PET. So in medical imaging reconstructions, first we have an image forward problem, so that models the acquisition. We start from an unknown object. We've got an imaging system, and through physics, we measured raw data, which are stored in a vector y. And the inverse problem goes the opposite direction. We start from the raw data, we have a reconstruction method, and we want to recover an image x. And the challenge is to be able to reconstruct high-quality images from noisy and or undersampled data y. So here I introduce the two image modalities I will be presenting in this talk. So first, computed tomography or CT. It's an X-ray based image technique that shows detailed body structure. So it's anatomical imaging. And then positron emission tomography or PET is a radiotracer based imaging modality that shows metabolic activity and, for example, to detect tumors or metastasis. So first, I start with the CT model. In CT, the image we want to reconstruct is the attenuation map mu, is the X-ray attenuation map, and this attenuation map depends on the energy, which makes the problem more complex. The measurements are stored in a vector y, which correspond to detected photons along each X-ray beam I. And the expected detection are given by the Beer-Lambert law, the polychromatic version of the Beer-Lambert law, which is integrated with the energy spectrum. And this is a very ill-posed problem because of all the energies. So to reduce the ill-posedness, we assume that the model is monochromatic and the image we reconstruct is an average attenuation image over the energy spectrum. And we have an approximate noise model. So we have a Poisson noise plus a Gaussian term, which models the electronic noise. So this is an approximated noise model. In photocounting detectors, the PCDs, they are different from, so this was for energy integrating detectors. So in PCDs, we have a different model, different from with EIDs, in the sense that we are counting the photons that we detect and we can measure the energy. And the detections are regrouped into energy bins, one bin per energy interval. We have the same Beer-Lambert law for each energy bin. And we have an exact noise model, which is Poisson, and this is very useful because we have better maximum likelihood estimates, so with less noise. Also, the PCDs are smaller than the EIDs, and which enable higher image resolution for reconstruction. Another key advantage of the spectral information in PCCT is we are able to do material decomposition. So instead of reconstructing a single attenuation image, we are capable of reconstructing multiple material images. So for example, we can have one image for bones, one for soft tissues, and one, for example, for iodine. And here iodine is usually used as a contrast agent as a surrogate for blood perfusion. And then these materials are integrated in the forward model through an operator that is a linear combination of the material density images with known material energy attenuation curves. In PET, we have a different model. So the object to reconstruct is lambda, the radioactivity distribution, and we've got measurements along each line of response. We measure the number of back-to-back gamma photons pairs, so along each line of response I. The expected detection, the forward model, there's an emission part and a attenuation part. The attenuation part depends on the gamma ray attenuation, and we also have to account for scatter and randoms. We have the same noise model, and the attenuation map is usually derived from CT or MR. And in absence of CT or MR, or just because we don't want to do CT or MR, we have to estimate lambda and mu simultaneously together from the emission data Y. And this is a very ill-posed problem, especially in absence of time-of-flight information. So here I introduce some notations. So X is the image to reconstruct, and it has a prior PDF P of X. We assume it has a prior PDF P of X. We've got the measurement vector with a conditional PDF. The forward model is the expected measurement, and we denote it Y bar. And standard image reconstruction is usually formulated as we want to find an image X such that the forward model matches with the measurement. Or equivalently, we can formulate it as an optimization problem with a loss function. And because we have an ill-posed problem, because we have noise, we want to add a regularization, which takes the form of a penalty term. And usually R is designed, or we hope this R mimics the prior probability function, so the negative log prior of the images. But typically, this prior is handcrafted, like for example, we use a TV prior or a qualitative prior. And when the prior is differentiable, the reconstruction is typically performed with a gradient descent algorithm. So now, say, for example, we do a standard acquisition. So we've got the patient here, the ground truth X, and we have a source that rotates around the patient. So this is for CBCT. We obtain a sinogram Y, and we retrieve the original image. We do a reconstruction and estimate by minimizing, by solving this optimization problem. So now say, for example, we want to reduce those. So we have the same patient, we have the same source trajectory, but we emit less photons per angle of view, and we obtain a noisy sinogram, so lower signal-to-noise ratio. And if we perform a reconstruction, we have more noise in the image. We can compensate for this by adding a regularization term. So we reduce the noise, but at the same time, we also reduce the resolution. Another approach consists of doing a sparse view acquisition. So we've got less position of the source. We obtain a sparse view sinogram, and we reconstruct the image, and we have strict artifacts due to the sparse acquisition. So we can compensate for that by adding a compressed sensing penalty term. So here, for example, T is the gradient, so it's a sparsity promotes the sparsity of the gradient. This reduces the artifacts, but also we have a loss of resolution. So we are in this situation. We want to reduce the dose on one hand, and on the other hand, we want to reduce the noise and also to preserve the resolution. But this is something we cannot do with conventional image priors, and that's why we want to use AI. We want to design better priors, or to train better priors that can beat the physics, and to be able to have these two at the same time. So I will now move to the type of model we use, the diffusion models. And before that, I will just highlight the difference between supervised methods and unsupervised methods. So supervised methods, they typically take as an input a degraded measurement or a degraded image and returns a high quality image. So those models have been widely used in the literature because they are simple to train, and also they have great performances. However, they required pair label data, so noisy, clean images, and also they can be sensitive to protocol or scalar differences, unless you're using a foundation model, which are very pricey. So on the other hand, we have unsupervised generative methods, and they don't learn mapping; they learn a prior distribution of the image. So they're useful because they require clean images only. We don't need pair data, and they can be combined naturally with forward models for image reconstructions. However, they tend to be computationally expensive for training and also for inference. So generative model, the idea here we consider the image space. The image space is a very high dimensional space, and most of the images in that space are irrelevant. And the images we're interested in, they lie somewhere in a submanifold. So this is an interpretation of what's happening there. And this manifold has a lower dimension. So how do we use generative models? We consider a latent space. This latent space in general has a lower dimension. And what we do is we sample as a latent variable in this space. We have a deep generator G theta, and it will map this Z somewhere on the manifold. So how do we train such a model? Assuming the data manifold lies on the line, we have training data, and we have a training data distribution. So it's an empirical distribution, which is a sum of the Dirac's on each of the training data sets. We sample a latent variable with a simple probability distribution. We use a deep generator, and the pushed forward distribution of the prior of the Z is the probability distribution of the generator, and we train it to be a continuous extension of the empirical data distribution. So that's how I like to see it. So there are three types of generative models in the literature. First, we have variational autoencoders. They are pretty stable, easy to train. They have a clear probabilistic interpretation. However, they tend to produce blurry images. An alternative are the GANs, generative adversarial networks, which have been pretty popular in the literature recently, over the last 10 years. They provide nice images and sharp with high resolution. However, they are unstable, difficult to train, and they are prone also to mode collapse. And the current alternative now that we have are diffusion models. They combine high visual quality and stable training, but they tend to be computationally expensive. So diffusion models, here I describe briefly diffusion denoising probabilistic models. So the idea is quite simple. We sample an image from the data set, and we gradually degrade the image with noise until we obtain pure white noise. And denoising, the decoding process consists of starting from white noise and gradually remove some noise until at the end we obtain a fully denoised image, which is sampled according with a distribution, which is a generalization of P data. And this also can be used for synergistic sampling for multi-channel images, such as RGB images or PET-CT, spectroscopy, etc. So how do we train and sample in diffusion models? So we know how to degrade the images because we know we have to add the Gaussian noise. However, the reverse PDF is unknown. And the key idea is that an approximate version of this reverse distribution can be expressed in terms of the score function through 2D formula. And this score is unknown. So what we do is we do score matching. We train the score we approximate it with a neural network, and we can see that training this score is more or less equivalent to training denoiser, which removes the noise, rejects as an input the noisy sample, and retrieve the original image. And then we use this train score, and we inject it into a reverse diffusion process, which takes the form of this algorithm. So we start from white noise, and we apply this denoiser, and we retrieve, we sample an image, a realistic image, starting just from noise. And there are like some faster alternatives like DDIM, which allows to use less time steps. So how to use this in image reconstruction? So instead, we would like to sample from a measurement, so to use a posterior distribution. So we use a conditional score given the data, and this conditional score can be written as a sum, so through Bayes formula, it can be written as a sum of the train score from the data, from the image data only, plus a conditional score y given xt, and this conditional score is used to drive towards data consistency. And then we have this algorithm DPS that we saw yesterday, diffusion posterior sampling, which, so on one hand, we've got the score that pulls toward the data manifold, and then we've got this conditional scores that pulls the estimates towards data consistency at each iteration. And when we look at this algorithm, we see it's very similar to a standard iterative reconstruction for variational methods. A big issue with DPS is that it's very computationally expensive. So there are several workarounds from the literature. One first workaround, so to process 3D data, is to decompose the volume into 2D slices and to perform diffusion on each slices individually and to add data consistency across the z-axis. So in practice, this works pretty well, but it fails at capturing the whole full 3D information of the volume. So another solution which has been very famous is to use a pre-trained autoencoder. So we encode the 3D images into lower dimensional images, and we train the diffusion model in the latent space with a lower dimension, and we perform inference in the lower dimension space, and we return the final image by applying the decoder. An alternative that we have been using lately in my group is to deploy a wavelet transform. So the wavelet transform maps the image into a space of the same dimension, except that we've got 8 channels, 8 for 8 of the 8 wavelet coefficients, and each of these channels has a lower dimension, and we process all those channels simultaneously. So which helps for parallelism and also to reduce memory bottlenecks. And then we inject this wavelet transform in the wavelet, this wavelet DPS formulation. So each iteration inference is performed on the wavelet coefficients, and we apply the inverse wavelet coefficients for data consistency with the projection data. And that's what we've been doing in the 3 applications I will present you now. I will start with the first application, so motion compensated head CBCT. So in CBCT, we've got motion blur if we don't account for this motion, and we have to estimate the motion jointly with the image. During reconstruction, we have to estimate motion and the image simultaneously. However, this type of approach requires a good initialization, which is not possible in sparse UCT due to the strict artifacts. So here I introduce first the motion operator, W of 5. So it's an image-to-image operator that maps the image to the image affected by motion. And it depends on some parameter phi, and this parameter can model rigid, also non-rigid motion if we want. And the standard joint reconstruction and motion estimation can be seen as a blind inverse problem. So we estimate at the same time x and y, x the image, phi the motion operator. And typically this is solved by an alternating minimization problem in x and phi. So we alternate between x and phi until convergence. And this requires a good initialization for x, but this is not possible in sparse view CT. So this motivates the question, can we derive a DPS-like approach to solve this problem? And the answer is yes. We just take the same, so here we use, so the method is called ADM for Adaptive Diffusion Model. And this is based on DDIM, so slightly different from DDPM before. And we just add a motion estimate during the reconstruction. So we treat this as a iterative reconstruction, and we update the motion parameter at each iteration, and we return the final image with the inverse wavelet transform. So I will show some results here. We've trained a model on a public data set of diagnosis CT images, and we simulated 60 and 20 view CBCT projections to perform reconstructions. So here I'm showing some results. On the left, we've got the FDK reconstruction. So FDK is a FBP-based method which has been modified for CBCT. And we see that the reconstruction, they suffer from obvious strict artifacts and also motion artifacts that we can see here at the edges of the skull. And then we perform also JRMTV, so joint reconstruction and motion estimation with a TV prior. So the images looks quite nice, although slightly smoother. And then all methods obtain the best results, so no artifacts and no motions artifacts. So here JS stands for jumpstart to speed up inference. Here we present the same results with the 20 view reconstructions, and obviously FDK fails completely, and JRMTV works, although we had to tune the TV prior to prevent strict artifacts, and the image is quite over smooth. And while for our methods, we are doing pretty okay. I'll move to the second application, so PCT material decomposition. In this case, we're working with multi-channel images, so bones and water. And the data are energy bin photon counts. So I think we've got 3 energy bins in this case. We've got the same forward model. And we considered 2 synergistic DPS approaches. So the first one is image-based two-step DPS, which consists of doing a synergistic DPS reconstruction of the attenuation maps at different energy levels, and then to apply the pseudo-inverse of the material to attenuation operator. So that's an inaccurate model because we have to discretize the energy levels, and this can provoke artifacts. And the other approach that we consider is one-step DPS, which is a synergistic estimation of the material images directly from the raw data. And I will show some results here. So, and we also compare with two supervised approach, so unit I, which is in image domain, and unit P, which is in the projection domain. And we've performed FBP simulation, low dose simulations. So we observed the FBP reconstructions are noisy as expected. The unit methods are doing okay. Regarding the DPS methods, so in the TDPS approaches, it's doing okay in the sense that we have no noise. However, we do suffer from crosstalks between activity and attenuation. Between bones and soft tissues, so that we see in the spine here. However, the DPS methods that use the accurate physical model doesn't suffer from these crosstalks. This is another experiment that we've performed on sparse view data, and we have pretty much the same results here. Another case that we've investigated is a hybrid model. Say, for example, that we have a diffusion model that we have trained on water and bones, for example, but we want also to use iodine also as a contrast agent, but we don't necessarily have patients with iodine in our data set, so we don't have a trained model. So here the idea is to perform DPS and assume that the two material images are independent, which is obviously not true, but we just assume they're independent for the lack of a better model. And because if we assume they're independent, then the joint score function can be written as the two scores which have been stacked together in a single vector. And then we approximate the untrained model, the untrained score, with a pseudo PDF, which can take the form of any variational regularizer that you want. So here, for example, we use a Huber prior. And then we have a hybrid methods, and in which so we have the standard DPS approach, in which we have plugged in this variational model for the iodine. And here I will show some results here. And so on the right, we've got the hybrid ODPS approach. So we've got nice bone and water decomposed images, and we can see that we can estimate the iodine, although the model was not trained with iodine. And also what we need to see is that this is not noisy because, so here the middle column is an LBFGS reconstruction without any prior, maybe with Huber prior. And we see that the noise in the soft tissues and the bone propagates into the iodine, which is not the case with hybrid ODPS because we've got nice diffusion models for the bones and the soft tissues. I will now move to the last application here, so CT-less PET. So in PET, we need CT because we need to do attenuation correction, and in absence of attenuation correction, we have biased, we cannot do quantitative PET because the reconstruction is biased. And we would like to do, we need to do attenuation correction, but the CT-derived attenuation correction will increase the dose, so increase the patient dose, so we want to reduce the dose, and eventually so we don't want to do a CT. So the idea is to do a joint reconstruction, so we estimate jointly the activity and the attenuation together. So this can be written as a standard joint JRAA inverse problem. And this is typically solved, again, with an alternative minimization in lambda and mu. So we estimate lambda, then mu, and so on, until convergence. However, this is very ill-posed in absence of time of flight information. Also, we need to estimate scatter alongside lambda and mu, because scatter is traditionally estimated from the attenuation image, which we don't have. So this motivates the question, can we derive a DPS approach for JRAA? And yes, we can. So we developed these methods. This method where we use a diffusion model for the activity, one for the attenuation, and the diffusion model was trained simultaneously for activity and attenuation, so the reconstruction is synergistic. And we also added a scatter update here, so we use a parametric model that depends on some parameter phi that is updated at each iteration. And at the end, we perform the inverse Fourier transform and we retrieve the images. So here I'll show some results on simulated data and also patient data. We compared with another method, which is called MLAA unit, which consists of doing a post-processing to guess the attenuation map from the non-AC images. So here are some results with high count data, and we see that all the methods are doing well, and our method is the method we propose, GRA-DPS, is doing pretty well. And also, what is important to note, that it works pretty well in absence of time-of-flight information. Another example here, where we reduce the counts to 1% of the counts of the previous experiment. And again, we see that our methods, GRA-DPS, is doing, I think, to me, is doing the best. And it also works in absence of time-of-flight information. And finally, I show this result on real patient data. This experiment, so this patient data, they were acquired also with non-time-of-flight. And again, we observed, I think, to me, the best results are with our method, GRA-DPS. Although the image was slightly blurry, so we had to do one additional OSEM iteration to refine the details in the activity image. So I've got some quantitative results in appendix, so I'm happy to share with you later if you want. So as a conclusion, I don't know in terms of timing how I've been doing. So there was a lot of cover, so I've been speaking pretty fast. So diffusion models, they enable high quality stable reconstructions across multiple tasks. They're quite convenient because they only required clean images for training, and the physics-informed sampling allows data consistency with the reconstruction. And we have demonstrated results on motion-compensated head CBCT, PCCT material decomposition, and joint activity attenuation in PET reconstruction. And regarding future work, well, the future is uncertain, but at the moment we're considering faster and cheaper diffusion methods. For example, to process full total body PET imaging in a high resolution using new type of encoders. We're also interested in parametric imaging and cardiac imaging with rubidium, for example, and also without CT, so in a joint activity and attenuation reconstruction framework. Some references I'm going to skip, and so here are my 4 PhD students who have been working on these 3 applications. So I would like to thank them. They've been working very hard, and also all my collaborators in France and also abroad. I would like to thank for all the discussions, and also the French National Research Agency as well for the fundings. And thank you.